start the recording. Yeah, I guess it started. All right. Yeah, thank you very much for coming. Today is the lecture number 7, and today we begin the new chapter. It's entitled Quantum Gates and Quantum Logic. So this is the chapter number 3, as far as I remember. Chapter 3, Quantum Gates and quantum logic. Quantum gates and quantum logic. And the subchapter 3.1 is the Bloch sphere. The Bloch sphere. So what is a Bloch sphere? So Bloch sphere allows us to represent the quantum state of any single qubit system. Basically, one qubit system, it gets the wave function, the arbitrary wave function of psi, which is equal to some lambda 0, right, plus beta 1. So this is the general psi vector of a qubit, and Bloch sphere helps us to represent this state of a qubit, of a single qubit. So in this expression, this alpha and beta are complex numbers, right? And the fact that they are complex means that we keep track of the phase of these particular states, 0 and 1. So we not only care about the amplitude, but also the phase of these states. But at this point, we can make a simple assumption that our alpha is actually real number, and the beta has some phase. Let's denote this phase phi. So this is the phase factor, and times the amplitude factor, let's denote it by b prime. So in this, as we define this alpha to be real and beta in this form, now we can assume that our alpha, beta prime, and phi, they are real numbers. So they are real, right? And on top of that, we have to take into account that we actually normalize this state of the qubit. So I just remind you that what that means. It means that the probability of finding the qubit in the 0th state and plus the probability of finding in the state 1 is supposed to be equal to 1, right? But now our alpha and alpha is real and beta is this expression above, so we conclude that alpha square plus this e to the power I phi beta prime square equals to 1, and so the modulus square of this exponential function is simply 1. So this gives me alpha square plus beta prime square equals to 1. So very simple expression. And at this point, I can I can a little bit rewrite this expression in order to include bring the angles or like other parameters to this analysis that will be actually the spherical coordinates. So let's recall this trigonometrical equation, which is sine square of x plus cosine of square of x is equal to 1, right? So we now comparing these two, this one, and conclude that if we, for example, assign alpha to be equal to some cosine of theta over 2 and beta prime to be sine theta over 2, then this trigonometrical equation is satisfied, right? Sine squared sine squared of theta over 2 plus cosine squared theta over 2 will like equals to 1. So we basically change the parameters, the variables from alpha and beta prime to sine and cosine theta. And and don't forget about this phase term also, this phase term. So now we can, introduce this, introducing these new variables. We can rewrite this the psi vector of the qubit in the following way. So it will be the psi vector is equal to alpha, which is a cosine theta over 2, plus e to the power of I phi times sine theta over 2. Oops, I forgot about the state. State 1. State 0. And plus e to the power of I phi sine theta over 2, state 1. Okay. So we started from two variables, alpha and beta, and ended by another expression with also two parameters, theta and phi. And and this is basically the same state, just expressed in other variables. And but now having this theta and phi, we can interpret them as spherical coordinates, right? So let's interpret theta and phi as spherical coordinates. Spherical coordinates. And what it means that we can plot any state of the qubit on the surface of a sphere, right, in these spherical coordinates, and this sphere is called the Bloch sphere. So we can represent any psi of a qubit as a vector in this three-dimensional space, or as a point on a sphere known as the Bloch sphere. Very important concept. So in this expression, the phi can be any number between 0 and 2 pi. And theta also can be any number, but in the range between 0 and pi. And as we can see from this expression, this phi is attributed to or describes the relative phase. Phi describes the relative phase. Relative phase between basically this term and the second term. If you count the phase like from the first term here, then the phase of the second one will be the relative phase between the two. And the second one, this theta, it determines the actual probability. Determines the probability. Probability of finding the qubits in a particular state. For example, I just remind you that the probability of finding, for example, the qubit in the 0 state is what? Is the modulus of the projection of the psi vector on the 0 state. Modulus square. Right. And from here, we conclude that it is defined by the cosine square of theta over 2, right? Because this inner product of 0 state and this psi state gives you this cosine theta over 2. So it will be cosine square of theta over 2. And similarly, the probability of finding the state 1 will be given by a similar expression, and it is defined by sine square theta over 2. So no phase here, and the phase actually not that important at this point when we're talking about the probabilities of one single qubit, but it is important in terms of the interaction of the qubits. Like if you have a system of several qubits, then you have to keep track of all the phases of all the qubits in your system, and the interaction will be actually will depend strongly on the relative phase between the qubits. But now we're talking about just one single qubit, so the phase is not that important. So as I said, now we can represent any state of a qubit in this as a point or vector in this Bloch sphere. The Bloch sphere. So let's represent this Bloch sphere. So let's draw the axis z, y, and x. Right. So this is x, this is y, and this is z. Let me draw the sphere like this. Okay, so this is my the Bloch sphere, And the general state of the qubit, let's write this again, it is cosine square theta over 2 plus e to the power of I phi sine, oops, I again forgot the states, sorry, the 0 state plus e to the power of I phi sine square theta over 2 state 1. Right. So, so let's first find where is the 0 state. The 0 state. The 0 state corresponds to what? We need to get this factor to be 1, right, and this one to be 0. So we conclude that the theta in this case must be theta must be equal to what? To be 0, because cosine of 0 is 1, sine of 0 is 0, and phi is basically any number. So theta in this block sphere, right? This is sphere, so maybe I should write or draw this like this. So this is sphere. And this axis x intersects this surface of the sphere, for example, in this point and this point. Yeah, so we introduce the radius vector in this in this sphere, like this, right? So it's denoted by R capital, and I count theta from this axis z. So this is my theta. This is theta, and phi is counted from the axis x. So this is phi. And the positive angle, like positive rotation in this space is the clockwise rotation. Right, so theta is equal to 0 phi any means that the point that I am after is this one. Right, so at this point, this vector r points like in this direction, and this direction is defined by theta of 0 and phi is any. So this is state 0. Next, where is the state 1? So the same way, I need to get my first term to be 0, the second to be 1, right? And I conclude that the theta in this case must be equal to pi, because sine of pi over 2 is equal to 1. And again, phi any. Phi is any. Where is this point on the block sphere? It is this point right here. This is state 1. Right. Next. Let's consider the superposition state, this state plus. I remind you that this is nothing but just linear superposition of the state 0 and state 1. So in this case, what theta and phi I need? So my theta in this case supposed to be equal to pi over 2, right? Because pi over 4, sine pi over 4 and cosine pi over 4 is equal to 1 over 2. And so this I get this normalization factor 1 over square root of 2. And yeah, and phi, so theta is equal to pi over 2, and phi equal to 0. Right, to make this the exponential factor, the phase factor to be 1. So where is this point on the block sphere? This point on the block sphere, pi over 2 and phi is 0, so this is this point at the axis x. So this is state plus. This is state plus. So next, the state minus, which is again the linear superposition of the same, but with minus over here. So it is 0 minus 1. So again, the theta must be equal to pi over 2, but phi supposed to be equal to pi, because I remind you that there is a Euler's formula, right, which is e to the power of e I phi. It's actually equal to cosine phi plus e sine phi. And when I plug in pi to this formula, I get cosine p gives me -1, and sine phi is equal to 0. So I get -1. Yep. And this point is actually this one. So this is the state minus, the superposition state minus. And so next, so let's consider this state plus I. So the state plus I is again the superposition of two states. So it's a square root of 2, and then here 0 state plus imaginary unit state 1. So this is the difference. The phase before the state 1. All right, so how I get this state? How do I get this state? So apparently the theta is supposed to be also equal to pi over 2, right? But the difference is the phi. So the phi in this case is supposed to be equal to pi over 2. Pi over 2 because, again, plug into this Euler's formula, pi over 2 cosine pi over 2 is equal to 0, sine pi over 2 1, so it left me imaginary unit there. So where is this point? Theta equals to pi over 2, so it's again in the xy plane. And 5 pi over 2 is here, this point. So this is the state plus I. State plus I. And finally, the last state minus I, it is nothing but this 1 over square root of 2, 0 state minus I, state 1. Again, theta supposed to be equal to pi over 2, and phi is equal to either minus pi over 2 or 3 pi over 2. 3 pi over 2. Right, so 3 pi over 2 sine 3 pi over 2 gives me minus I. So this this state is located here. So this is state minus I on this Bloch sphere. Bloch sphere. Very good. Yeah, by the way, important point here to mention is that Bloch sphere is not the Hilbert space, right? Obviously, because, for example, in Hilbert space, these states are 0 and 1 or plus and minus, they are orthogonal. So if I would represent them in the Hilbert space, I would draw the orthogonal vectors. In fact, in this Bloch sphere representation, these orthogonal vectors are collinear, right? They are collinear. So yeah, let's make this note, because it's quite important note. On the Bloch sphere, on the Bloch sphere, the angles are twice as large, as in the Hilbert space. As in the Hilbert space. For example, 0 state and state 1 orthogonal. In Hilbert space, but collinear on the sphere, but collinear on the sphere. Do you have any questions about?
So far, so good.
So far, so good. Very, very good. So let's go then to the next subchapter, chapter 3.2, named Quantum Gates and Quantum Circuits. Quantum gates and quantum circuits. Quantum gates and quantum circuits. So first of all, what is basically a circuit model, right? The circuit model is a sequence of some building blocks that carry out elementary computations called gates. So gates elementary computation, elements or building blocks, elementary computations, elementary computations, elementary computations, and the circuit or circuit model, the sequence of gates, right? For example, in classical logic, we have a number of logic gates, namely seven gates. So let's write this down. Actually, so in classical logic, we have seven basic logic gates. Basic gates. For example, gates AND, gates NOT, XOR, etc. etc. And for example, this gate NOT. Let's consider this gate NOT. What it does. So this is the single input, single output gate. Single input, single output, single input, single output gate, denoted by the element like this. Right, sometimes we put 1 inside, and if we denote this input and output A and Q, we can construct the truth table. Truth table of this gate. So A and Q. So what the gate NOT does, it basically inverts or flips the byte, right? The bit. For example, if I have 0 in the input, in the output I get 1, and if I get 1 in the input, in the output I get 0. Very simple. Very important like point to notice here is that this gate is reversible. So NOT is reversible. Reversible. It means that if I take, for example, 2 of these gates, not 1, not 2, what I will get? I will get basically the identity, right? So my 0 will turn to 0, 1 will turn to 1. Why? Because the first gate turns, for example, for 1 in input, I get 0 in the output, but the output of the first one is the input of the second, so it is 0, and finally I get 1. I have 1 in input, and I get a 1 in output. So it's reversible, reversible gate, reversible classical gate. And of course we have like other types of classical gates, and the more complicated gate is 2 input, 2 outputs. For example, this XOR gate, it is 2 inputs, 2 input, 1 output. 2 input, 1 output gate, denoted by the element like this. So we have these 2 elements as inputs, like A and B. This is XOR here, and the output Q. Right. So the truth table for this classical gate is as follows. So this is A, B, and Q. And what this gate basically does is the following. So so basically, when the both inputs, the A and B, are equal, for example, if A is equal to 0 and B is equal to 0, the output is 0. And the same way, if input 1 be 1, my output also will be 0. But if the inputs are different, like A is equal to 1, B is equal to 0, then the output is 1. The same way here. Right. So important point to notice here is that XOR is irreversible. Irreversible gate because, for example, say I detect 1 in the output, then I don't know what is my input, 1 0 or 0 1. So I have some lack of information. I need some extra information to make it reversible. So XOR gate is irreversible. And for classical logic, classical computation, this is okay. But in quantum logic, all operators must be unitary. as far as we remember, in quantum logic, all operators must be unitary. It means that the product of the operator by its Hermitian conjugated is equal to 1, right? So it means that the corresponding gate must be reversible. So all gates must be reversible. And I just remind you why it's important. It's important because if I have the product of two vectors, like inner product of two vectors, the unitary operator doesn't change this inner product, because this guy is identity operator. Right. So like if my initial state was normalized, then after application of the quantum gate, which rotates or changes this this vector in Hilbert space or in the block sphere representation, the normalization of this vector doesn't change. Like if my initial vector was of the length of the vector was 1, then after the operation it will be left unchanged. It will be equal to 1. So at this point, let's consider several single qubit gates. Single qubit single qubit gates. Single qubit gates. What it means? It means that these gates are they act on a single qubit. This is the quantum analog to the single input, single output gate in the classical logic. So the first qubit we consider is called X qubit. Excuse me, X gate. It's also denoted by, or can be denoted by, sigma X. Also can be denoted by px. Depending on the literature, depending on the author, there is no settled terminology here, or not terminology, but the letter we use to represent this gate. So X gate, which is sigma X, px, it is defined by sigma X Pauli matrix, which is 0, 1, 1, 0. And in the outer product representation, it is this element 1, it is 0, 1 element, so this 0, 1, plus element 1, 0, 1, 0, right? So this is the X gate. And from here we see that this gate, what it does, it basically flips the gate. Why? Because if I apply this gate, this X gate on a state 0, for example, the product of this element with state 0 gives me state 1, and the product of this one with state 0 equals to 0. So I left with the state 1. Let's actually write this down. So X, for example, acting on the state 0, what it is, nothing but 0, 1 plus 1, 0 times state 0. It's equal to 0, 0, 1, 0 plus 1, 0, 0. Right. So the first term is equal to 0 because state 1 and 0 are orthogonal. So it gives me a state 1. State 1. And the same way, application of this X gate on the state 1 gives me 0. That's easy to see. So this is the bit flip gate. Bit flip gate. Right. Bit flip gate. because it, like, in some sense, it takes the 0 and flips this to 1. Of course, this is not a bit now, it's a state, but like terminology is taken from the classical computation. Bit flip gate. Yeah, and also we can say that this is the classical, or excuse me, the quantum analog of NOT gate. Analog of NOT gate in classical logic. In classical logic. Let's take another another state and act this X gate on a state. let's say state plus. What I will get? I will get state. I mean this operator X, which is 0, 1 plus 1, 0, and it acts on this superposition state 1 over square root of 2, and then 0 state plus 1 state, right? So it is equal to 1 over square root of 2, and now I see that my 0 must be, I mean, the only product of this one and this one gives me non-zero element, so it will be 1 for the first one, and for the second one it is 0. So basically this is the 0 plus 1, so this is exactly the same state. So this state didn't change after application of the X gate. And the same for minus, of course. So application of X minus also gives minus. But what about the application of X gate on a plus I? So let's check this. This is 0, 1 plus 1, 0 for the gate, and it acts on this state plus I, which is 0 plus I state 1. All right, I get 1 over square root of 2, and here I will get 1, then plus I, let me see. Plus I times 1. Okay. Okay, 1 over square root of 2, then the state 1 plus I state 0 and state 0. So it reminds the state plus I, but what I do now, I take the imaginary 1 from the brackets, and I get I 1 over square root of 2, and here I get 0 minus I state 1, right? So it's equal to I over square root of 2. Well, it's equal to I, and the state is minus I. State is minus I. So and the same basically for the state minus I. If I apply my the x gate on the state minus I, what I'll get? I will get the state plus I. So it's easy to see because the gate x is unitary, right? So I just return to the initial state, right? So from this analysis, I see that what this gate basically does, it rotates the vector state in the Bloch sphere representation over axis x by angle of pi, 180 degrees rotation. So it is flips 0 and 1. It flips the plus I and minus I, and like leave unchanged the state plus and minus. Let's write this down. So in the Bloch sphere, representation, x gate rotates the vector state, we denoted by r vector. This is the vector state around axis x by pi, or 180 degree clockwise. So the next gate, the second one. So the second gate is we consider is Z gate, or also known as sigma Z, or also known as PZ. Again, depending on the literature, you can meet like any of these. And so the matrix of this gate is Z Pauli matrix, which is 1, 0, 0, minus 1. We considered this matrix some time ago, right? And the eigen elements, eigen values of this matrix are 1 and minus 1. This matrix is diagonal. In the outer product representation, I can write the same this way. So this is the 0, 0 element minus element 1, 1. 0, 0, 1, 1. So let's take this Z gate and act on the Z state, for example. What I'll get? Oh well, from this representation, I see that what I will get is actually the same state 0. And what if I act Z state on 1? I will get basically minus the same state. So what changes? Only the phase of the state, but let's say the probability of finding this state doesn't change at all after application of this Z gate. So it leaves unchanged the states 0 and 1. But what about, for example, the state plus? Let's figure out that. So my operator z is 0, 0 minus 1, 1. And the plus state is 1 over square root of 2, state 0 plus state 1. I'll get 1 over square root of 2. And then the product of this one and state 0. And then minus state 1, which is nothing but the state minus. So Z gate flips the plus and minus. Again, since this this gate is Hermitian, I can simply, I conclude that after application Z on the state minus, I will get initial state plus. And well, in the same way for these states plus I minus I, I also get the basically change of the or flip of this state. From plus I will get minus I up to the phase prefactor, and again application the same to the minus I returns the state to the plus I. So from this I conclude that my Z gate, what it does, it rotates the state vector around the axis Z, again by the angle pi or 180 degrees in the clockwise direction. Oh, by the way, I forgot to mention that the schematical presentation of this gate X, right, is simply this. So this is the like a rectangle with X inside. This is how we denote this gate in the circuits. For the Z gate, I have basically the same notation with Z inside, and as we just figured out, the Z gate rotates the state vector around the axis Z by angle pi. Angle pi. So it's very easy to see what happens in this block sphere representation, right? So I find this axis Z, and then when I rotate this sphere around Z axis, the state 0 and 1 don't change at all, and the states plus and minus, they flip, and plus I minus I, they also flip. Yeah, so it's very easy to to memorize how these gates work. Do you have any questions? Okay, so the next one is gate Y, also known as sigma Y or PY. Again, it's represented by the sigma Y Pauli matrix, which is 0 minus I 0. and in the outer product representation it is minus I01 plus I 1 0 1 0. Okay, let's figure it out. Let's figure out what this y gate does. So let's again take this 0 state and after application this y gate, what I'll get the change of phase represented by this imaginary unit and the state 1. So it flips the state and also adds this phase factor. And acting this gate on state 1, I'll get minus I0, right? So it flips the state. And let's consider as another example acting of this gate on a plus state. So it will be minus I01 plus I10, the gate, and then the state 1 over square root of 2, the 0 state, and the state 1 superposition. So I can take 1 over square root of 2 in front of this expression, and then for the product of 0, I mean acting this gate on the state 0, I'll get I state 1, and the 1 I'll get minus I state 0, 1 state 0. Okay, I can take the I out from the parenthesis and also minus 1, so I'll get minus I and state minus. Yeah, so it flips the states 0 and 1 plus and minus and now we see that behavior is follows this logic. So this is the y gate, so it rotates the state vector around axis y, and in result of this rotation state 0 and 1 flips, plus and minus flip, but the states plus I and minus I don't change. For example, y plus I, in the result I'll get state plus I, basically the same state. So this this y gate, what it does rotation around axis y by pi or 180 and change the phase. Change the phase, that is not like important for single qubit systems. So this is about x, y, and z gates, and now let's consider another one which is actually very important. Number 4. The fourth gate is called Hadamard gate. Hadamard gate. Hadamard gate. So the Hadamard gate is represented by the matrix matrix H, and it's equal to 1 over square root of 2, and the matrix 1 1 1 minus 1. Let's frame this formula, this operator. On the other hand, in the outer product representation, this Hadamard gate is equal to 1 over square root of 2, right? And then 0 0 matrix element, then plus 0 1 plus 1 0 minus 1 1. So this is the outer product representation. So why this this gate is important? To demonstrate that, let's consider the action of this gate on a state 0, right? So from the product of state 0 on this gate H, this Hadamard gate, what I will get 1 over square root of 2, of course, this prefactor, and then this first element, which will give me 0 state, and this element here, which is state 1. State 1. So what I'll get, what I have gotten, I have the state 1. No, oh, sorry. This is state plus. State plus. And the same way, the action of the Hadamard gate on a state 1 gives me 1 over square root of 2, 0, minus 1, right? Which is state minus. So the action of Hadamard gate on the 0 and 1 states basically creates the state of superposition. So Hadamard gate creates the superposition. So H, Hadamard gate, creates the superposition. Yeah, which is pretty important fact. So in the quantum circuits, the Hadamard gate is represented by this element with H, and we can also denote that it creates the superposition state, right? And vice versa, since Hadamard gate is unitary, right? You were supposed to check that in your homework. So the the double action of Hadamard gate on a state gives you the identity. So the action, for example, Hadamard gate on a state plus returns you 0. So Hadamard gate not only creates the superposition, but also takes superposition and returns the state either 0 or 1 in this basis. And well, why it's important? Important because it creates the superposition and of the states of a single qubit, which is important for the computations, and also it is useful, for example, if you can if we can do the measurement in the z basis, right? Z basis means that we can measure the state 0 or 1, right? So this is called z basis. So if you can measure the system in the state 0, the system in the z basis, but cannot do their measurement in the for example, in the axis. Then what we do, we first apply the Hadamard gate on the state in the x basis, for example, x or plus or minus state, and then, or I mean superposition of those, and then that returns or transforms the state to the z basis, and then we can do the measurement. Let's write this down. So it is useful. It is useful. For example, if we can do z measurement or measurement in z basis, but can't do x measurement. So we first apply the Hadamard gate on the state. It flips or it transforms the state to the z basis, and then we do the measurement in the z basis. And another example or another reason why the Hadamard gate is important, let's consider as an exercise. So let's consider, or let's do this exercise. So the exercise is to show that the following is true. So x gate can be represented as the following product of h gate, z, and another h. So what this formula says is that if you have the z gate but don't have x gate, you can take z and h gate and combine them together, and in the result you will get the x gate. So yeah, let's demonstrate that. So first let's show that the product of z and h I mean, let's find this product of z and h. Z is equal to 1 0 0 minus 1. The h is 1 over square root of 2 1 1 1 minus 1. Right. So the product is, let's take this 1 over square root of 2 out, and now rows by columns. So 1 times 1 1, 0 equals 0, so it is 1. Next, 1 plus 0, which is 1. Next, 0 minus 1 is minus 1 is equal to minus 1, and finally minus 1 is equal to 1. Right, so this is for ZH. And now for the HZH, I'll get 1 over 2 now, and H is 1, 1, 1 minus 1, and ZH is 1, 1 minus 1, 1. Right, so it's equal to 1 over 2. Here 1 minus 1 is 0. 1 plus 1 is 2. 1 plus 1 is 2. 1 minus 1 is 0. Right, so it's equal to 0, 1, 1, 0. And this is nothing but the X gate. So this is proved. So we see that like having one gate, for example Z, and the Hadamard gate, we can construct X gate by taking the product of the two, and one can also like show that taking the product of, for example, Y and Hadamard gate, you can, or Z or X, you can basically create the other gates. Yeah, this basically means that in practice you don't need to realize all three Pauli gates. You can realize just two, and then by combining them with Hadamard gate, you can create the third one. The third one. So this is the number 4. So the next gate, number 5, and it's called P gate. Let's consider this P gate. It's also known as phase gate. Hence this capital letter P capital. This P capital, it gets parameter phi, and is represented by the following matrix: 1, 0, 0, and then the exponential e to the power of I phi. Right. So instead of minus 1 here, as in the gate Z, right? Now I have the parameter phi, so basically the angle. So and so as you can see, it's connected to Z gate. Like if my phi is equal to pi, I get exactly this Z gate. So what this P gate actually does, it also does the rotation of the state vector around the axis Z, but by this arbitrary phase phi. So it does rotation around Z by phase phi, by arbitrary phase phi. Right, so this is the phase gate, P gate, and as a particular example or particular case of this phase, sometimes we introduce this like another gate S gate, which is nothing but the P gate for phi to be pi over 2. Pi over 2. So it's equal to 1, 0, 0, and then e to the power of I pi over 2 gives me I. So this is the matrix. Or in the out product representation, it is 0, 0, and plus I 1, 1. Right. And in this way, we can find any any results of application of this gate on any state and build the logic basically. So this is the S gate. Again, it rotates the state vector around z-axis, but by the angle pi over 2 or 90 degree. And also we sometime introduce another gate. Let's number 5.2. It's called T gate. Similarly, T gate is just P gate, but for phi of pi over 4. So rotation by pi over 4. And it's equal to what? It's equal to this matrix 1, 0, 0, e to the power of I pi over 4 here. Again, this is just rotation over axis z by pi over 4. And sometimes people also introduce this most general type of single qubit gate. It's called U gate. We can also like highlight this one. So the U gate is just the generalization of all gates that we discussed so far. So it gets three parameters: theta, phi, and lambda, and it's given by this matrix cosine theta over 2. The second element is minus e to the power of I lambda sine theta over 2. Then e to the power of I phi sine theta over 2. And finally e to the power of I phi plus lambda cosine theta over 2. So this matrix basically takes into account all gates, all matrices that we discussed so far. So this is the most general, most general single qubit gate. Most general single qubit gate. And for example, if if theta is equal to pi over 2 and phi is equal to 0 and lambda is pi, this matrix gives me the Hadamard gate. Or if my theta and phi is equal to 0 and lambda is arbitrary, this gives me the phase gate P. So I bring this U gate because I mean we often meet this one in the literature, so it's instructive to bring this to the for the completeness of the story. So this is about single qubit gate. Single qubit gate has one input, one output, and yeah, and of course it's unitary. So if I apply this gate just twice, then I ideally I have to get identity. For example, like in experiment, my gate is always some real physical system, right? And this system acts or conducts some transformations to the signal that comes to this gate, let's say this way, and in output I get something different, like output from the system. And how can I check the fidelity of this gate? How can I check if my gate works perfectly, or the way I expect this gate to act? Compare this with theoretical case. Well, we can often put two exactly the same gates, put them together, and what I expect to see in output is exactly the result of the input, right? And of course, it is not the case in general, because in realistic systems we have loss, we have noise, etc. But at least we can compare the result with the theoretical prediction, what we would expect to see in the perfect case, and figure out what is the fidelity of my what is the fidelity of the gate. So this is about single qubit gate. Let's talk about now the 2 qubit gates. So 2 qubit gates. So in fact we will discuss just one 2 qubit gate, because for example, in classical computation theory, classical logic, we know that any computer can be built using just how many? Probably seven logical elements. I don't remember that. And there is a theorem in quantum computation that says that any type of quantum algorithm can be realized using just three qubits, two single qubit gates, not qubits, gates, sorry, two single qubit gates and one 2-qubit gate. So we need 1 qubit gate. And the 2-qubit gate, it is a gate that acts on a system of 2 qubits, right? So now we have to recall what we discussed last time, last lecture about multi-qubit systems. Let me briefly remind you. So last time we discussed basically how we discussed the system of several qubits and how we use this operation of tensor product operation to combine the two qubits, right? We take the product of the Hilbert space that corresponds to each qubit, and we also combine the operators. So the resulting operators will be the like more complicated matrices. For example, if we talk about the 2 qubits, the system of 2 qubits, then the resulting operators will be matrices 4 by 4 instead of 2 by 2, as in the case of one single qubit. In the system of 2 qubits, the resulting operator will be a system of 2 or 4 by 4, and the state vectors become the matrices, well, the vectors with 4 elements, right? And we concluded the lecture by this discussion of the Bell states. So we say that the Bell state is the most entangled state. It is non-separable state. You cannot represent the state as a product of two states like that belong to the each qubit, each single qubit, right? And yeah, so this is the quantum entanglement. We'll discuss this effect of quantum entanglement in like more deeply in what follows. But now let's talk a little bit about these 2 qubit gates. So the system of the psi vector of 2 qubits in a most general psi vector of 2 qubits will be the expression like this. So it will be C00 state 00, right? Then element C01 state 01 plus state 10, or the element 10, vector 10, and finally the coefficient 11 state 11. So in this basis of these two vectors of the states of 2 qubits, I mean, I just remind you that, for example, this state 01, for example, is nothing but the tensor product of state 0 and state 1. which is, how do I find this? So it is vector 1, 0 for the first qubit, right? And then tensor product 0, 1 for the second qubit. And then how this tensor product works, I just take the product of the first element by this vector, the second vector, and second element again by this this vector. Or it is nothing but, I mean, I just take the product of this constant 1 by vector, so it is 0, 1, and then 0, 0, 0, right? So this is the this is the basis vector, the new one of the combined system. And in this four-dimensional Hilbert space, it became four-dimensional because I have the tensor product of two-dimensional Hilbert spaces, right? So in this four-dimensional Hilbert space, the psi vector, the vector state of the system of two qubits, right, is given by this vector of elements C00, C01, C10, C11. So this is my new vector. Instead of vector of two elements, now I have vector of four elements. Vector of four elements. All right. Yeah. For example, let's consider this first Bell state. For example, the first Bell state. The first Bell state is this disentangled state 0, 0 plus 1, 1. Or if I rewrite these states in the form of column vectors, right, it is 1 over square root of 2, and then the first one is 1, 0, 0, 0, and the second one is 0, 0, 0, 1. Right, this is the state 0, 0, and this is the state 1, 1. And what I get 1 over square root of 2 and then vector 1, 0, 0, 1. This is how we work with the state vectors of two qubits. State vectors of two qubits. And the two qubit gate, which acts on states like this one, that we consider, is so-called C0 gate. C0 gate. Let's indicate that this is the two qubit gate. So C0 two qubit gate. C0 two qubit gate. C0 also known as CX. CX gate. Or C sigma X gate. This C here stands for controlled. So this is like X gate, which is bit flip gate, but controlled. Like somehow we control how we flip the qubit using this gate. So in the quantum logic, this C0 gate is given by this graphical representation. So we have two qubits. That's why I draw two lines for the first qubit and for the second qubit, right? And then I do this shaded big dot, and on the other end, it's like a circled cross inside, something like this. And this is the logic. This is the this is the logic. So how this qubit works? So let's figure out that. Yeah, but by the way, sometimes we also draw this like this. Oops. So one gate, one qubit, second qubit, Cx inside, or C0, qubit 1, qubit 2, qubit 1, and qubit 2, but put prime because it will like change. And one qubit here is called control qubit. So it's a control qubit. And the second one is target. So control qubit apparently is a qubit that controls the target, controls the target one. And so let's build the truth table. Here, so we have two qubits: control qubit, target qubit, and an output of the target one. So this Q2 prime. No need to specify this Q1 because Q1 doesn't change, but Q2, this second qubit, changes. The target qubit changes. And the logic here is as follows. So if my control qubit is 0, the target qubit doesn't change. Like, say, if my target qubit was 1, the output will be 1. If target qubit was 0, the output is 0. If target is 1, the output is 1. Doesn't change. Before and after. It's like this gate is like turned off, right? The input at these two qubits, Q1 and Q2, is equal to the output. Nothing changes. But when the control qubit is 1, the state of the target qubit flips. For example, if my target qubit is in 0 state, it flips to state 1, and vice versa. From state 1, it flips to state 0. this is this is how it works. For example, if I take my CX gate and I act this gate on a state, let's say 0, 0, 0, 0. So now in this expression, I have to assume that this first state in this double state of the entire system, the first state is control, and the second one is target. So I conclude that, well, since my control gate is 0, my target gate doesn't change. So my output is simply 0, 0. Nothing changed. But if I act this CNOT gate on this double qubit state, let's say 1, 0, so now this control gate is 1, and that means that my target qubit has to be flipped. So in this case, I'll get 1, 1. And likewise, if I act on the state 1, 1, again, my control is 1, so I have to flip target, so I'll get 1, 0. This is how it works. I mean, in terms of the matrix representation, the matrix that like corresponds to all these operations is this one, so it will be 4 by 4 matrix. 4 by 4 matrix. 1, 0, 0, 1 here, then 0, 0, 0, 0 here, 0, 0, 0, 0 here, and here 0, 1, 1, 0. So 4 by 4 matrix, I enumerate these elements 0, 0, then 0, 1, then 1, 0 element, 1, 1, and likewise here 0, 0, 0, 1, 1, 0, 1, 1. So, and it consists of 4 submatrices, right? The first submatrix is basically identity. The second and third are 0 matrices, and the last one is X, this X matrix, the Pauli X matrix. That's why it is control X. Control X. That's why it is control X. Again, I can represent this this CNOT matrix in form of outer product of the vectors, and in this case it will be state 0, 0 times 0, 1, excuse me, 0, 0, 0, 0. Then it will be 1, 0, 0, 1, 0, 1, 0, 1, 0, 1. Then 1, 0, 1, 1. And finally, the last non-zero element is 1, 1, 1, 0. 1, 1, 1, 0. Right? So 0, 0, 0, 0, then all elements are 0, then 0, 1, 0, 1, then 1, 0, 1, 1, and finally 1, 1, 1, 0. Okay, looks good. Yeah, so we have considered how this control X gate or CNOT gate applies on the on these basis states, but how it applies or how it operates with the arbitrary matrix. So I remind you that arbitrary matrix is not matrix, the vector, right, in this double qubit space. It is vector, column vector C00, C01, C10, and C11, right? And when I apply my CNOT gate on this state C00, C01, C10, C11, the procedure here is exactly the same. So I assume that my first index is the control, and the second is target. Means that if my signal is not signal control index is 0, the target doesn't change. So these two elements don't change. But then the first one of this is 1. So my control is 1, and I have to flip the target. So this element turns to C11, and this one turns into C110. This is the result. This is the result for the arbitrary 2-qubit state vector. And finally, as a like last point for today, let's consider the simplest quantum circuit. So this example simple 2-qubit quantum circuit. Simple 2-qubit quantum. So this is simple 2-qubit quantum circuit, but in the same time, it is very important quantum circuit, and it actually gets this name of golden 2-qubit gate, 2-qubit circuit. Sorry, golden 2-qubit circuit. Why golden? Because like it's very important for applications. So what this is about? So let's consider 2 qubits, qubit 1, qubit 2. So Q1, Q2, right? And first, I apply the Hadamard gate on the first one. So this is my Hadamard gate, right? I remind you that Hadamard gate takes the state and creates the superposition of two states, right? So after this point here, I will get the superposition of two states. And then after Hadamard gate, I apply this C0 gate here. C0 gate here. Well, so the shaded dot is connected to the upper qubit. So this is the control qubit. And then this one is target qubit. So let's suppose that initially I have my qubits in the state 0 and 0. Upper is 0, lower is 0. What I'll get. So before Hadamard gate, yeah, and I apply these gates like from leftmost to the right, so in like in this direction. So Hadamard gate applies first, then to the result this second one, the C0 gate, applies to the result of application of Hadamard gate. So the state 0 is this column 1 0, right? So the application of Hadamard gate on state 0 creates the superposition state of 0 and 1, which is state plus, right? So in this point here, after Hadamard gate, my upper qubit is in this superposition state. So this is the first qubit. But the second qubit still in the state 0 in this point, because so far no two qubit gates applied, so my qubits are not entangled yet. They didn't interact yet, so I consider them not entangled, right? But then this two qubit gate applies, and it applies to the state of two qubits combined, right? In order to get this, I have to write the tensor product of two. The first one is in the state in the state plus, then tensor product and state 0. Again, this is the first qubit, this is the second qubit before C0 gate, right? So it's equal to 1 over square root of 2 0 0 plus 1 and times, because they didn't interact yet, so it's state 0. So the result is 1 over square root of 2 and this 0 0 plus 1 0 0 0 1 0. This is separable state, right? I can represent this state as a product of two, plus state and 0 state. So this is not entangled state yet. But then this C0 gate comes to the story. C0 gates comes to the story. So Cx gate applies on this 1 over square root of 2 0 0 plus 1 0 state, right? What I'll get, 1 over square root of 2, of course, here, and then the upper is control. So for this one, control is 0. So my target doesn't change. So it will be just state 0, 0 here. And then plus, for the second one, my control qubit is 1. And now it means that I have to change to flip the target qubit. So this target qubit will be flipped to state 1. So in result, I get state 1, 1. So after application of this of these two gates, Hadamard gate and CNOT gate, I got what? I've got this first Bell state. First Bell state. One over square root of 2, 0, 0 plus 1, 1. Right. So this result. And this is remarkable because now I see how the application of one 2-qubit gate, this CNOT gate, allows me to create the entangled state, basically so it's an entangled state, right? So the use of 2-qubit gate, in this case this is CNOT gate, allows me to create the entangled state. My initial state was 0, 0, but after application of this circuit, this quantum circuit, I've got the most entangled state, which is Bell state. Yes, and these states are non-separable. These states are not separable and very important for many applications that we will discuss in what follows. So this is the end for today. Let me stop the recording.